except that now what I'll try to do is that go into some of the challenges actually. And there are far too many challenges, so I won't be able to cover all of them in the 25 minutes. I may rush through some of them, but more than that, what I've tried to do is that try to put as many as I can on these pages and not go through details, and that's again something that we'll be doing over the discussions. So this is the outline, overview of some of the surveys and data holdings that we have, various data types that we have. By data types, I mean not the Python-like data types, but just how the kinds of holdings that we have. And I see Matthew mumbling that maybe he's going to say some of these things, but there are going to be commonalities all over. Variability searches, and that's, I think, where if one is looking for variability, only a small fraction of objects, astronomical objects, are variables, and if one wants to find them early, how can one go about doing that? And different people use different things. We have found that something like Stetson J is useful, but then you cannot use it as a single parameter over the entire data set and so on. So coming to use specific data sets, specific techniques, but then being able to combine them in a homogeneous fashion is something that's going to be a big challenge, especially when we have very large data sets. And period finding is another thing. If you have got a very good data set, if you have got a very good time series, then period finding is not too difficult, but most of the times we are not in that regime, so we need to be able to find periods even when the data are horrible. But we should be able to do as best as we can and go on from there. So how to go about doing that? Combining surveys is another crucial thing. Again, as I said before, most surveys have specific aim, and then that aim defines how the survey happens. And yet when there are multiple surveys, there are ways of combining the data sets. And that is a powerful way of using all those data sets together. And how can we go about doing that? And combining classifiers. There are a large number of classifiers. Rather than let them work on their own, how can one try to combine them in meaningful ways? So snapshot of the surveys that we have. Here is CRTS, for instance, which has been observing for more than 14 years, most of the sky, both in the northern hemisphere and the southern hemisphere. It doesn't use filters. PTF, for the last several years, it has been covering large part of the north sky. Gaia started observing a couple of years back. It's going to have fewer number of observations, only about 70 in 5 years, but it has low resolution spectra, and of course the astrometry is going to be fantastic. So as you can see, the types of data that these surveys get are very different from each other, and we should be able to find good ways of combining them. And of course, as I mentioned in the previous quick discussion, LSST, which will be coming on, it's going to have, it's one of the main things that it'll be doing is that it'll go very deep, and it'll have a large number of objects that it'll be observing. So how to be able to classify that at the rate at which LSST will be finding things is going to be a challenge. So what is it that surveys do actually? Most of the times they're after low-hanging fruit. They're designed for specific things. They're going after that. They try to select the best objects that they have, and I have called it easy science. It's not really easy. I'm just trying to be overreaching in terms of saying about the low-hanging fruit. So they define something, and when you define it, if you do the survey well, then that science becomes easy. But much of the rest of the science still stays hard, and being able to get to that. So again, many surveys then do a little bit of spectroscopic follow-up. This is great. You get to know what those specific kinds of objects are, and that does push the envelope, but also it leaves a large number of gaps because you cannot do spectroscopy for more than a few objects. It's a very expensive thing compared to imaging and most of the other data that we get. So that is something that we'd like to get away with, and one way to do that is through machine learning, statistics, and so on. So with LSST, what we're going to have is that there are going to be 1,000 observations each 30 seconds. So that seems a lot, but it's over 10 years. And if you have the 10-year timeline along this room, for instance, which is about 10 meters, then only 1 millimeter of that will be actually covered by the observations. So 1,000 times 30 seconds over 10 years is going to be a really small fraction of time that we'll be looking at any given object. And that's the kind of that data that we'll have in order to try to classify that. Today's holdings again, so with CRTS we have several 100 million light curves, and there are 1 billion cutouts. These are being served from IUCAA right now, so almost all the data are public here. With PTF, which is partly public, there have been some data releases. It's multi-filter, unlike open. And the CRTS cadence is designed for asteroids, so it's lumpy, so you take 4 images within 30 minutes, and then don't take another set of observations for maybe a week sometimes. So it becomes very chunky, lumpy that way. Then there are various data sets like for streaks from nearby asteroids with PTF, with Pan-STARRS and Gaia. These are again multi-filter, and there have been small data releases. Over the next few years, we'll see more. But with Kepler, it's very interesting. It's a very small area, but these time series are very non-sparse. So they're ideal if you want to start designing some algorithms, which then you may want to go on to sparser time series. So you have a very good labeled data set that you can get. But again, because the area is small, then you do not have very large number of objects there. And then we'll hear a little bit more about pulsar timing arrays in this workshop too. We are not going to go into exoplanets here. That's what Kepler does a lot with. So there's a whole set of methodology with those that is out there. And then again, quick properties for light curves that we have. This is of course a very extreme light curve, but in general, the time series that we have are very gappy. There are huge gaps, as I mentioned. They're very irregular. So if you're looking at financial time series, then you can do many, many things really well, because every morning the market opens, and then you have got observations, and then it closes, and then it again opens, and so on. Not so with astronomy data. So you cannot use data or techniques directly from any of those other things. And then again, the error bars tend to differ for various reasons, including the atmosphere itself. So all those issues make the time series that we have in astronomy likable by many statisticians. They love the data because they present new challenges, and some of those challenges are what we'll be looking for here. And errors are ignored by many methods as well. So trying to bring those in, trying to have more methods use errors will be a great thing. And again, the sparsity of the time series. So you don't have to read the axis here, but this is several years worth of data and a few points in each year. But compared to that, the Kepler time series from a very small fraction of that time period, and you have got a very large number of points. So these ones you will want to try to combine. And the interesting thing is that if you look at a single light curve, if you look at a small portion for the same object, then depending on where you are looking at it, it can look very different. And so if you are getting features, statistical features from those, then they're going to look very, very different. And that's the kind of thing that one is trying to look at. So not very different from the elephant and the blind people trying to see what the elephant is. So our time series are in a way like that. Right, meaning for that particular outburst, the dwarf nova, it is, so what combinations we have. So there is, in fact, a subgroup on light curve decomposition. So when you see a light curve, you can have various things contributing to that. And if you're looking at only a section, maybe that particular phenomena is more active, and that's what you're seeing at the time.
Previous slide, what were the different points?
Okay, sorry, yeah. So each of these points is an observation, and you see the error bars there, and the ones that are in red are upper limits. So at that time we were looking in that direction, but we did not see that object. And then by knowing what aperture we have, we can say that if it was, the object must have been there because we see it over a long time. So what is the brightest that it was? We can say that, and then the line indicates that. No, same instrument. It's by the same instrument, yeah. This is a homogeneous light curve. This is from CRTS, so no filter open. And then.
How can there be upper limit and rejection?
No, not at the same time. But as I said again, with CRTS, we have got 4 observations within 30 minutes. So it may happen that you see it now, but 10 minutes later you don't see it. So that's the kind of variations that you can have because it's a variable or because it's a transient. Rarely you can have asteroids passing through, but in this particular case, because of the large number of detections, we know that it was a static object. So. And then the upper limits are different at different times, again, because of atmosphere, for instance. Right? And so one of the things that has happened for the last several years is that given a time series, you get various features, you derive various statistical features and try to use those statistical features for clustering, classification, and so on. So Richards et al. Had this paper where they used non-sparse Ogle and Hipparchus time series data, and they defined a bunch of things. Simple things like amplitude, what's the difference between the magnitude and the minimum? Then you could divide it by 2, for instance, and so on. So that is one of the features that simply tells you how variable that object is likely to be, because most objects that we see, more than 90% of the objects are not variable